The meter, or meter, is the base unit of length in the International System of Units. The SI unit symbol is m. The meter is defined as the distance traveled by light in a specific fraction, about 1/300 millionth of a second. The meter was originally defined in 1793 as 1/10 millionth of the distance from the equator to the North Pole. In 1889, it was redefined in terms of a prototype meter bar. In 1960, the meter was redefined in terms of a certain number of wavelengths of a certain emission line of krypton 86. In 1983, the current definition was adopted. In 1959, the imperial inch was redefined as 0.0254 meters. 1 meter is about 3 3/8 inches longer than a yard, i.e., about 39 3/8 inches. Spelling. Meter is the standard speaking of the metric unit for length in all English-speaking nations except the USA, which uses meter. Measuring devices are spelled meter in all countries. The word meter, signifying any such device, has the same derivation as the word meter, denoting the unit of length. Etymology. The etymological roots of meter can be traced to the Greek verb mu epsilon tau rho epsilon omega and noun mu epsilon tau rho o micron nu, which were used for physical measurement, for poetic meter and by extension for moderation or avoiding extremism. This range of uses is also found in Latin, French, English and other languages. The motto mu epsilon tau rho omega chi rho omega in the seal of the International Bureau of Weights and Measures, which was a saying of the Greek statesman and philosopher Pittacus of Mytilene and may be translated as use measure, thus calls for both measurement in moderation. History of definition. In 1668, the English cleric and philosopher John Wilkins proposed in an essay a decimal-based unit of length, the universal measure or standard. In 1670, Gabriel Mouton, Bishop of Lyon, also suggested a universal length standard with decimal multiples and divisions, to be based on a 1-minute angle of the Earth's meridian arc or on a pendulum with a 1-second period. In 1675, the Italian scientist Tito Livio Burattini, in his work Misura Universal, used the phrase metro cataleo, derived from the Greek mu epsilon tau rho o micron nu kappa alpha theta omicron lambda iota kappa omicron nu, to denote the standard unit of length derived from a pendulum. As a result of the French Revolution, the French Academy of Sciences charged a commission with determining a single scale for all measures. On 7 October 1790 that commission advised the adoption of a decimal system, and on 19 March 1791 advised the adoption of the term meter, a basic unit of length, which they defined as equal to 1/10 millionth of the distance between the North Pole and the equator. In 1793, the French National Convention adopted the proposal. This use of meter in English began at least as early as 1797. Pendula in 1668. Wilkins proposed using Christopher Wren's suggestion of defining the meter using a pendulum with a length which produced a half period of 1 second, known as a seconds pendulum. Christian Huygens had observed that length to be 38 Rhineland inches or 39.26 English inches. This is the equivalent of what is now known to be 997 millimeters. No official action was taken regarding this suggestion. Meridional. In the 18th century, there were two approaches to the definition of the standard unit of length. One favored Wilkins' approach, to define the meter in terms of the length of a pendulum which produced a half period of 1 second. The other approach was to define the meter as 1/10 millionth of the length of a quadrant along the Earth's meridian, that is, the distance from the equator to the North Pole. This means that the quadrant would have been defined as exactly 10 million meters at that time, with the total circumference of the Earth defined as 40 million meters. In 1791, the French Academy of Sciences selected the meridional definition over the pendular definition because the force of gravity varies slightly over the surface of the Earth, which affects the period of a pendulum. To establish a universally accepted foundation for the definition of the metre, more accurate measurements of this meridian were needed. The French Academy of Sciences commissioned an expedition led by Jean-Baptiste Joseph de Lambry and Pierre Metchain, lasting from 1792 to 1799, which attempted to accurately measure the distance between a belfry in Dunkirk and Montjuïc Castle in Barcelona to estimate the length of the meridian arc through Dunkirk. This portion of the meridian, assumed to be the same length as the Paris meridian, was to serve as the basis for the length of the half-meridian connecting the North Pole with the equator. The problem with this approach is that the exact shape of the Earth is not a simple mathematical shape, such as a sphere or oblate spheroid, at the level of precision required for defining a standard of length. The irregular and particular shape of the Earth smoothed to sea level is called a geoid, which literally means Earth-shaped, but does not correspond to the actual shape of the Earth, but rather is a mathematical model of its shape. Despite these issues, in 1793 France adopted this definition of the metre as its official unit of length, based on provisional results from this expedition. Prototype meter bar in the 1870s, and in light of modern precision, a series of international conferences was held to devise new metric standards. The Metre Convention of 1875 mandated the establishment of a permanent international Bureau of Weights and Measures to be located in Chevreuse, France. This new organization was to construct and preserve a prototype meter bar, distribute national metric prototypes, and maintain comparisons between them and non-metric measurement standards. The organization created such a bar in 1889 at the First General Conference on Weights and Measures, establishing the international prototype meter as the distance between two lines on a standard bar composed of an alloy of 90% platinum and 10% iridium, measured at the melting point of ice. However, it was later determined that the first prototype meter bar was short by about 200 micrometers because of miscalculation of the flattening of the Earth, making the prototype about 0.02% shorter than the original proposed definition of the meter. Regardless, this length became the standard. The original international prototype of the meter is still kept at the BIPM under the conditions specified in 1889. Number of wavelengths of red-orange emission line of krypton 86 in 1893. The standard meter was first measured with an interferometer by Albert A. Michelson, the inventor of the device and an advocate of using some particular wavelength of light as a standard of length. By 1925, interferometry was in regular use at the BIPM. However, the international prototype meter remained the standard until 1960, when the 11th CGPM defined the meter in the new international system of units as equal to 1,650,763.73 wavelengths of the orange-red emission line in the electromagnetic spectrum of the krypton 86 atom in a vacuum. Distance traveled by light in a specified time to further reduce uncertainty. The 17th CGPM in 1983 replaced the definition of the meter with its current definition, thus fixing the length of the meter in terms of the second and the speed of light. The meter is the length of the path traveled by light in vacuum during a time interval of 1700829979924580000299,792,458 of a second. This definition fixed the speed of light in vacuum at exactly 7082997924580000299,792,458 meters per second. An intended byproduct of the 17th CGPM's definition was that it enabled scientists to compare lasers accurately using frequency, resulting in wavelengths with 1/5 the uncertainty involved in the direct comparison of wavelengths, because interferometer errors were eliminated. To further facilitate reproducibility from lab to lab, The 17th CGPM also made the iodine-stabilized helium-neon laser a recommended radiation for realizing the meter. For the purpose of delineating the meter, the BIPM currently considers the Henna laser wavelength, lambda Henna, to be 700263299121258000632.99121258 nanometers with an estimated relative standard uncertainty of 69892100000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 one limiting factor in laboratory realizations of the meter, and it is several orders of magnitude poorer than that of the second, based upon the cesium fountain atomic clock. Consequently, a realization of the meter is usually delineated today in labs as 70067980076204201579800.76204.2 wavelengths of helium-neon laser light in a vacuum. The error stated being only that of frequency determination. This bracket notation expressing the error is explained in the article on measurement uncertainty. Practical realization of the meter is subject to uncertainties in characterizing the medium, to various uncertainties of interferometry, and to uncertainties in measuring the frequency of the source. A commonly used medium is air, and the National Institute of Standards and Technology has set up an online calculator to convert wavelengths in vacuum to wavelengths in air. As described by NIST, in air, the uncertainties in characterizing the medium are dominated by errors in measuring temperature and pressure. Errors in the theoretical formulas used are secondary. By implementing a refractive index correction such as this, an approximate realization of the meter can be implemented in air, for example, using the formulation of the meter as 70067980076204201579800.76204.2 wavelengths of helium-neon laser light in vacuum, and converting the wavelengths in a vacuum to wavelengths in air. Of course, air is only one possible medium to use in a realization of the meter, and any partial vacuum can be used, or some inert atmosphere like helium gas, provided the appropriate corrections for refractive index are implemented. The meter is defined as the path length traveled by light in a given time, and practical laboratory length measurements in meters are determined by counting the number of wavelengths of laser light of one of the standard types that fit into the length, and converting the selected unit of wavelength to meters. Three major factors limit the accuracy attainable with laser interferometers for a length measurement: uncertainty in vacuum wavelength of the source, uncertainty in the refractive index of the medium, least count resolution of the interferometer. Of these, the last is peculiar to the interferometer itself. The conversion of a length in wavelengths to a length in meters is based upon the relation, which converts the unit of wavelength lambda to meters using c, the speed of light in a vacuum in meter per second. Here n is the refractive index of the medium in which the measurement is made, and f is the measured frequency of the source. Although conversion from wavelengths to meters introduces an additional error in the overall length due to measurement error in determining the refractive index and the frequency, the measurement of frequency is one of the most accurate measurements available. Timeline: the 8th of May 1790, the French National Assembly decides that the length of the new meter would be equal to the length of a pendulum with a half period of 1 second. The 30th of March 1791, the French National Assembly accepts the proposal by the French Academy of Sciences that the new definition for the meter be equal to 1/10,000,000th of the length of a quadrant along the Earth's meridian through Paris. That is the distance from the equator to the North Pole. 1795 Provisional Metab constructed of brass. based on Bessel's ellipsoid, and legally equal to 443.44 lines on the Toise du Peru. The 10th of December 1799, the French National Assembly specifies the platinum meter bar, constructed on the 23rd of June 1799 and deposited in the National Archives, as the final standard, legally equal to 443.296 lines on the Toise du Peru. The 28th of September 1889, the first General Conference on Weights and Measures defines the meter as the distance between two lines on a standard bar of an alloy of platinum with 10% iridium, measured at the melting point of ice. The 6th of October 1927, the 7th CGPM redefines the meter as the distance, at 0 degrees Celsius, between the axes of the two central lines marked on the prototype bar of platinum iridium, this bar being subject to one standard atmosphere of pressure and supported on two cylinders of at least 10 mm diameter, symmetrically placed in the same horizontal plane at a distance of 571 mm from each other. The 14th of October 1960, the 11th CGPM defines the meter as 700,650,763.73 wavelengths in a vacuum of the radiation corresponding to the transition between the two p10 and 5d5 quantum levels of the krypton 86 atom. The 21st of October 1983, the 17th CGPM defines the meter as the length of the path traveled by light in a vacuum during a time interval of 1,299,792,458 of a second. 2002, the International Committee for Weights and Measures considers the meter to be a unit of proper length and thus recommends this definition be restricted to lengths which are sufficiently short for the effects predicted by general relativity to be negligible with respect to the uncertainties of realization. SI prefix forms of meter. SI prefixes are often employed to denote decimal multiples and submultiples of the meter, as shown in the table below. As indicated in the table, some are commonly used, while others are not. Long distances are usually expressed in km, astronomical units, light years, or parsecs, rather than in mm, gm, trademark, pm, m, zm or ym. 30 centimeters, 30 meters, and 300 meters are more common than 3 decimeters, 3 decameters, and 3 hectometers, respectively. The terms micron and millimicron are often used instead of micrometer and nanometer, but this practice is officially discouraged. Equivalents in other units. Within this table, inch and yard mean international inch and international yard, respectively, though approximate conversions in the left-hand column hold for both international and survey units. Means is approximately equal to means equal by definition, or is exactly equal to 1 meter is exactly equivalent to 10,254 inches, and to 10,009,144 yards. A simple mnemonic aid exists to assist with conversion, as 3/3s. 1 meter is nearly equivalent to 3 feet 3 3/8 inches. This gives an overestimate of 0.125 millimeters. However, the practice of memorizing such conversion formulas has been discouraged in favor of practice and visualization of metric units. The ancient Egyptian cubit was about 0.5 meters. Scottish and English definitions of the L were 941 millimeters and 1143 millimeters, respectively. The ancient Parisian toys were slightly shorter than 2 meters, and were standardized at exactly 2 meters in the measures USUL's system, such that 1 meter was exactly 1/2 toys. The Russian Vistar was 1.0668 kilometers. The Swedish mill was 10.688 kilometers, but was changed to 10 kilometers when Sweden converted to metric units.